Section 16 of the Science, History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 2, edited by Francis Rolt Wheeler. Geology, Chapter 8, Vulcanism, Part 2. The division of fragmental products includes all the materials which are ejected from the volcano in a solid state. These are of all sizes and shapes, from huge blocks weighing many tons, down to the most impalpable dust, which the wind will carry for thousands of miles. The more violently explosive the eruption, the greater the proportion of the lava that will be blown into fragments. In such eruptions as that of Krakatoa, all of it is thus dispersed and none remains to form lava flows. Cindiary fragments thrown out of the vent are called scoria, while portions of still liquid lava thus ejected will, on account of their rapid rotation, take on a spheroidal form and are called volcanic bombs. Lapilli are smaller, rounded fragments, and volcanic ash and dust are very fine particles, though with a wide range of variation in size. The term ash is so far unfortunate that it implies combustion, but nevertheless it accurately describes the appearance of these masses. In the immediate neighborhood of the vent, fragments of all sizes accumulate, but the farther from the volcano, the smaller do the fragments become. The coarser masses around the vent form a volcanic agglomerate, in which the fragments are of all shapes and sizes, heaped together without any arrangement. More regular sheets of large angular fragments form volcanic breccia, and these may be seen on a grand scale in the Yellowstone National Park and in many other parts of the Rocky Mountain region. The finer accumulations of ash, formed at a greater distance from the vent, are roughly sorted by the air and often quite distinctly divided into layers, while, as already explained, the muds on drying set into quite a firm rock, called tuff or tufa. It is important to emphasize the vast quantity of material which, in many volcanic eruptions, is brought from the interior of the earth and deposited on the surface. Thus the eruption of Skraptar Jökull in Iceland in 1783 produced an amount of lava which is calculated as exceeding 6 cubic miles in volume. The fragmental materials derived from the great explosion of Krakatoa in 1883 are estimated at 4.3 cubic miles, while for that of Tambora in 1815, Verbeek gives the almost incredible figures of 28.6 cubic miles. As the ejections flow off or fall more or less symmetrically around the vent, the form of a volcanic peak necessarily tends to become conical. The cone of Vesuvius consists mostly of cinders and is accordingly steep, nearly 40 degrees. Etna, about 10,000 feet high, and Mauna Loa in Hawaii, nearly 14,000 feet, consisting of lava streams, have an average slope of less than 10 degrees. A tufa cone is midway between these two extremes. From the days when Werner and his followers declared volcanic action to be caused by subterranean beds of inflammable material taking fire, speculation has been constant as to the underlying reasons that promote the heat expressed by volcanoes. The contraction of the earth in consequence of its secular cooling was the conception that met with the greatest favor, especially since Cordier calculated that were the earth to contract 1 millimeter, or 1/25th of an inch, it would suffice to cause 500 eruptions, each ejecting 1,300,000,000 cubic yards of lava. By common consent, geologists have recognized that the source of volcanic energy must be sought in the high temperature of the interior of the globe. They agree that the main proximate cause of the ordinary phase of eruptivity, marked by the copious evolution of steam and the abundant production of dust, slags, and cinders from one or more local vents, is obviously the expansive force exerted by vapors dissolved in the molten magma from which lavas proceed. Whether and to what extent these vapors are parts of the aboriginal constitution of the Earth's interior, or are derived by descent from the surface, is, however, a question on which opinions differ. Professor Skurmak and others have been led to conclude that the gaseous ejections are essentially portions of the original constitution of the magma of the globe, and that to their escape the activity of volcanic vents is due. On the other hand, since so large a portion of the vapor of active volcanoes consists of steam, many geologists have urged that this steam has in great measure been supplied by the descent of water from above ground, as it percolates down cracks and joints and infiltrates through the very pores of the rocks. It appears to be probable that, somewhat like the reservoirs in which hot water and steam accumulate under geysers, the subterranean magma receives a constant influx of water from the surface, which cannot escape by other channels, but is absorbed by the internal magma at an enormously high temperature and under vast pressure. In the course of time, the materials filling up a volcanic chimney are unable to withstand the upward expansion of this imprisoned vapor or water substance, so that, after some premonitory rumblings, the whole opposing mass is blown out and the vapor escapes in the well-known masses of cloud. Meanwhile, the removal of the underlying column relieves the pressure on the lava underneath, saturated with vapors or superheated water. This lava, therefore, begins to rise in the funnel until it forces its way through some weak part of the cone or pours over the top of the crater. An obvious objection to this explanation is the difficulty of conceiving that water should descend at all against the expansive force within. But Daubree's experiments have shown that, owing to capillarity, water may permeate rocks against a high counter pressure of steam on the further side, and that, so long as the water is supplied, whether by minute fissures or through pores of the rocks, it may, under pressure of its own superincumbent column, make its way into highly heated regions. The great physicist, Professor Arrhenius of Stockholm, has done much to clarify the views superincumbent upon modern investigation. Pointing out the amazing potency of force possessed by water vapor at a temperature far above the critical point, he notes that the magma is charged with this and compares the explosive discharge of lava and viscous matter in volcanic vents to the ascent of water in a geyser. At a depth of 540 meters, the vapor in the magma must press upward through the molten mass in gas bubbles, and as it escapes, the column of liquid is forced upward, sometimes even with explosive violence. At the end of the eruption, all the water in the lava column must again be in equilibrium down to that depth, and if no other agency intervened, the molten rock would gradually cool and stiffen so that no further discharge would take place in that funnel. But observation shows that eruptions may continue constant at the same spot for centuries and, as at Stromboli, may be as frequent as those of geysers. The gaseous water above the critical temperature, in consequence of the enormous pressure, 1,000 atmospheres at 10,000 meters down, beneath the surface, may have the same density as liquid water, probably rather less, and will press into the magma. The investigations of recent years have shown, moreover, that superheated subterranean water possesses entirely different properties from those above ground. At about 300 degrees, it is estimated that water and silicic acid are about equally strong, but at 1,000 degrees, water is some 80 times, and at 2,000 degrees, about 300 times stronger than that acid. It is a common error to criticize the inability of geologists to explain these matters, and the inexpert reader is very apt to declare that all that is necessary to be known is the nature of the interior of the earth, and all the phenomena of volcanism will arrange themselves in due consequence. In this the casual observer is right, but he forgets that a cognition of the interior of the earth in the present state of scientific investigation is so far impossible. The deepest boring ever made is less than 1/300th part of the earth's radius, and this was in the form of a hole a few inches in diameter. To give an illustration which may show the cause of the little knowledge of the earth's interior. Suppose the smallest insect visible to the human eye to be resting on the surface of an orange, and suppose this tiny insect again to be possessed of a boring instrument like the mechanisms of man, only of course comparable to its own size, that is to say, microscopic to the eye of man. If this insect should force this tiny borer into the orange, it would not penetrate the outer orange-colored skin of the fruit, much less would it reach the white rind within, while the pulp beneath the rind would forever be distant from its mental grasp. If, however, some inner stress in the orange should cause a fissure, through which the juice within should ooze out, in what manner could the insect, supposing it possessed of equivalent mental powers with man, explain the emission of the juice from its knowledge of the orange-colored cuticle of the fruit? In similar wise, the geologist of today is in no position to declare the nature of the interior of the earth from the slight scratchings that have been made upon the surface of the earth by such means as mines, wells, and so-called deep borings. He has not even reached the rind, much less the pulp within. From observations with the pendulum and plumb line, it is calculated that the specific gravity of the earth as a whole is 5.6, while the average specific gravity of the rocks, which form the accessible parts of the crust, is only 2.6. It follows that the interior of the globe is composed of much denser materials than the superficial portion, and this fact, together with the phenomena of terrestrial magnetism, has led many to the belief that the earth is substantially a globe of some dense substance, such as iron. Volcanoes, which eject molten and white-hot lavas, and thermal springs, which pour out floods of hot and even boiling water, indicate that the interior of the earth is highly heated, at least along certain lines. But this only reveals a strata of intense heat and does not prove the heat of the entire interior. It has long been known that, after passing through a zone of variable temperature, the heat increases with the depth below the surface. In New York, the rate is 1° Fahrenheit for every 50 feet, and in Prussia, where the deepest borings have been made, it is 1° Fahrenheit for every 60 feet of descent. Should this rate be continued regularly, it would reach, at the depth of 35 miles, a heat sufficient to melt almost any known rock at atmospheric pressure. Yet a depth of 35 miles, in comparison with the diameter of the earth, is almost a negligible quantity. Opinions concerning the internal constitution of the earth differ very radically, and only within the last few years has evidence begun to accumulate which permits the drawing of certain inferences with a considerable degree of probability. Many hypotheses as to the condition of the earth's interior have been proposed, to which the following are the most important. 1. That the earth is a molten globe covered only by a relatively thin crust. 2. That it is substantially a solid body. 3. That the interior passes gradually from a solid crust to a gaseous core, heated beyond the critical temperature, and yet under such enormous pressure that the core is as rigid as a solid body, but still a gas in molecular condition. According to this theory, the temperature of the earth at the center is about 180,000 degrees Fahrenheit, and the pressure 3 million atmospheres. 4. That it has a very large solid nucleus surrounded by a layer of fused material, upon which the crust floats in equilibrium. William B. Scott deals with these hypotheses as follows. 1. The first, or thin crust hypothesis, is now almost entirely abandoned, for there is really no evidence in its favor and very much against it. The velocity and character of the earthquake waves and the astronomical relations of the earth as a planet, especially the tidal phenomena, are strongly opposed to this view. 2. The earth is substantially a solid body is the opinion held at present by many geologists and astronomers. In support of it may be cited the astronomical evidence just mentioned, and the earthquake waves, the speed of which requires a medium more rigid than steel, while the very transmission of the transverse or distortional waves would seem to require a solid medium. 3. Between the second and the third hypotheses, the distinction is one not easy to explain in an elementary manner, and there are many modifications of the latter. According to Arrhenius, the rigidity of the earth is greater than less than that of steel, but the interior forms an extremely viscous mass, with qualities somewhat like those of asphalt at a low temperature, of pitch, sealing wax, and glass. These bodies behave under forces of deformation, which act quickly or with constantly changing direction, like solids, but under slow, continuing pressures, acting in a constant direction, they behave like fluids. Observations and records of very distant earthquakes show that when the path of the mass waves penetrates to a depth of more than 3/5 of the Earth's radius, the transverse waves of distortion are either extinguished or greatly retarded. This points to a change in the character of the medium and decidedly supports the notion of a gaseous core postulated by this hypothesis. 4. The fourth hypothesis, which assumes the presence of a fused layer between the crust and the solid nucleus, with gradual transitions from one to the other, is believed to avoid the astronomical objections to a molten globe, as well as certain geological difficulties in accepting the hypothesis of an entirely solid Earth. The earthquake observations, so frequently cited, are decidedly opposed to the belief that a layer of actually fused matter can exist at a moderate depth below the surface. It is thus probable that below the superficial crust, only a few miles in thickness, the great mass of the Earth is composed of very dense material, which transmits elastic waves like a very perfectly elastic solid, and yet is so highly heated and under such enormous pressure that it is potentially fused and liquefies under sufficient release of pressure and yields plastically to slow, long-continued stresses which act in a constant direction. Furthermore, there is evidence that a core, 2/5 of the Earth's diameter and composed of matter in a different state of aggregation, which may be gaseous, occupies the center. The important theory of isostasy is to be considered with care. It has been defined by Titman and Hayford thus: the Earth is composed of heterogeneous material, which varies considerably in density. If this heterogeneous material were so arranged that its density at any point depended simply upon the depth of that point below the surface, a state of equilibrium would exist, and there would be no tendency toward a rearrangement of masses. If the heterogeneous material composing the Earth were not arranged in this manner at the outset, the stresses produced by gravity would tend to bring about such an arrangement, but as the material is not a perfect fluid, the arrangement will be imperfect. The excess of material represented by that portion of the continent which is above sea level will be compensated by a defect of density in the underlying material. The continents will be floated, so to speak, because they are composed of relatively light material, and similarly the floor of the ocean will, on this supposed Earth, be depressed, because it is composed of unusually dense material. This particular condition of approximate equilibrium has been given the name isostasy. The recent very extensive and exact operations of the United States Coast Survey have brought strong confirmation of the theory of isostasy. The United States is not maintained in its position above sea level by the rigidity of the Earth, but is in the main buoyed up, floated, by material of deficient density. End of section 16.